Section 4.4 Concavity and curve sketching. So first definition, the graph of a differentiable function y equal f of x is concave up on an open interval I if derivative of that function is increasing on I. So concave up means graph should be look like this. This is called concave up. Here the first derivative is increasing. Concave down means graph look like this. Here the first derivative is decreasing. So that's the definition. So how do you find either first derivative is increasing or decreasing? That's where we need second derivative test. That's called the second derivative test for concavity. So a function f of x should be twice differentiable to use this second derivative test, and if the second derivative is positive on any open interval, then graph of that function on that open interval would be concave up. So if you would like to find out either graph is look like this or not, then find out the second derivative, and if it's positive, the graph should be concave up, and if it's negative, then graph should be concave down. And so wherever graph changes concavity, let's say from it's going from concave up to concave down or concave down to concave up, that point is called point of inflection. A point is just a notation, c comma the value of the function at c. This is just a point where the graph of a function has a tangent line and where the concavity changes is a point of inflection. Okay, at a point of inflection, either second derivative would be 0 or second derivative does not exist. So if you would like to find out the point of inflection, meaning where you would like to find out where the graph is changing its concavity, then you need to find out the second derivative. If you cannot find second derivative at any point, that is the inflection point. Or if the second derivative is 0 at any point, then that is your inflection point. For example, look at this graph. So this graph is concave down here first, and then after that concave up. So at this point, this concavity is changing. So this point is called point of inflection. But you can only find that point of inflection if you have the value of this function. So you find the first derivative, you find the second derivative, equate that second derivative to 0 and solve for x or the variable, and that's how you find this point. This is another example, and here you have a function f of x, and you can find out the point of inflection here, find out the first derivative, find out the second derivative. If you try to find out the first derivative here, it will be 5 over 3 x 5 over 3 minus 1 by using the power rule, which is basically 5 over 3 times x to the power 2 over 3. If you try to find out the second derivative here, it will be 5 over 3 times 2 over 3 x 2 over 3 minus 1, which is basically 10 over 9, which is x to the power minus 1 over 3, which is 10 over 9x to the power 1/3. So look at here, the second derivative at point 0, it doesn't exist because at 0 the second derivative is undefined. That's why this is the point of inflection. Okay, so the point of inflection means where either second derivative is equal to 0 or second derivative does not exist. So as you can see that this second derivative does not exist at 0. That's why it's a point of inflection. Sometimes you might have a point like this, where first derivative and second derivative is not possible. You cannot find the first derivative and second derivative for this function. The same way, we found here, the second derivative at 0 is not possible. Similarly, if you try to find out the first derivative and then second derivative, you cannot find the value of this first and second derivative at 0. That's why it's a point of inflection. So there is a second derivative test for finding the local maximum or minimum value. So for that, suppose second derivative is continuous on an open interval that has a point C, then uh, if the first derivative at that point is 0 and second derivative is negative, then the function has local maximum at C. Okay, because you can see that second derivative negative means the graph would be concave up. Okay, concave up. If you go back to this one, if second derivative if second derivative is negative, then graph is concave down. So I was wrong here. If the second derivative is negative, then graph is concave down, this one. And then because the graph is concave down, and then there is a point where the first derivative is 0, so that means you are going to get this kind of point, and that is your local minimum point, sorry, local maximum. So this is local maximum, local maximum, and this is local minimum, local minimum. So we just have to use the second derivative test for finding the local maximum or local minimum. So first find out the first derivative, and then find the second derivative, find the first derivative, and then solve this equation and find out the point where the first derivative is 0, and check what happens to the second derivative at that point. If the second derivative is negative, then that point the function has a local maximum at that point, okay, by using this second derivative test. If the second derivative is positive, then function has a local minimum at that point. If second derivative is 0, then this test doesn't, we cannot use this test for finding the local max or local min. Okay, so this section is basically about graphing. So we are going to plot a graph of a function. For plotting a graph, we are going to use this steps. First of all, whenever you try to plot the graph, find out the domain of the function, and then if it's possible, find out the symmetricity, meaning x-axis symmetry, y-axis symmetry, or origin symmetry. Then after that, find out the first derivative and second derivative. By using those derivatives, find out the critical points, uh, if you can, if any, and identify the function's behavior at each one. So after finding the critical points, you need to find out either the function has local maximum or local minimum at those points, and also find where the curve is increasing, where it's decreasing, by using the first derivative. You can also always say if the first derivative is positive, then curve is increasing. If the first derivative is negative, then curve is decreasing. And then find the point of inflection. For finding the point of inflection, you find the second derivative, equate that to 0 and solve, and wherever that second derivative is 0 or undefined, that gives you the point of inflection. If it's possible, identify any asymptotes. You already know how to find the horizontal asymptote, vertical asymptote, and oblique asymptotes. And then now, by using all this information, try to plot key points such as the intercepts and then points found in steps 3 to 5, and sketch the curve together with any asymptote that exists. So you have to use all this information to plot the graph. And eventually, these are some cases. You can see this is the graph of a differentiable function. This is smooth, connected, there is no jump. Sometime graph rise, sometime graph falls. Here the first derivative is positive, that means graph always rises because the function is increasing. Here the first derivative is negative, that means graph should fall because the function should be decreasing. Here, because second derivative is positive, that means graph could be look like this or look like this because both of them are concave up. If the second derivative is negative, then graph could be look like this part or this part because both of them are concave down. Here, as you can see that the second derivative up to this point is positive, and after that point it's negative, meaning it's concave up, and then at this point it's going to split to the concave down, meaning this point is point of inflection. And here, you know derivative changes sign, from it goes from positive to negative. That's why you have a local maximum value, from negative to positive local minimum value. So the derivative, first derivative is 0 and second derivative is uh, uh, second derivative is negative, so that means it's a local maximum. And if the first derivative is 0 and second derivative is positive, that means it's a local minimum. So these are the some possibility, while you plot the graph of a given equation or given function. So I'm going to do one problem from uh, your homework, directly from your my lab math homework. So let's see, this is the problem you need to do. Graph the function y equal x square minus 2x minus 8 by identifying the domain and as symmetricity, finding the derivative y prime and y double prime, finding the critical points, and identifying the function's behavior at each one, finding where the curve is increasing and where it is decreasing, finding the points of inflection, determining the concavity of the curve, identifying any asymptotes, and plotting any key points such as intercepts, critical points, and inflection point. Then find coordinate of absolute extreme points if any. So here basically, in this problem, we're using all the steps we have here. Okay, so we don't have to remember these steps for solving problem like this, because it's already given here. So we're just going to follow the steps here. Okay, and then I might need some space to write down, so I'm going to use this one here. Okay, so the first question is find the domain of the function. Look at the function. This is a polynomial function. The domain of the polynomial function is all real number, so that means it's going from negative infinity to positive infinity. So the domain is all real number. Basically this is parabola, so you already know the graph, but we're just going to follow the steps. Okay, and whatever way we do this problem, we are going to use the same way for rest of the problem in this section. Same idea, you might have different equation or different function. Okay, so that's a domain. The second thing is identify any symmetricities. So you can use symmetricity, for example, for finding the, let's say this is a problem 1. For finding the symmetricity, if you have a function f of x, which is x square minus 2x minus 8, we find f of negative x, which is negative x whole square minus 2 times negative x negative 8, which is x squared plus 2x minus 8. So now symmetricity can be found by comparing the value of the function at negative x. If it's equal to f of x, that's called even function, that's symmetric with respect to a y-axis. If it's equal to negative of f of x, that is odd function, which is symmetric with respect to origin. And we can also have symmetricity with respect to the x-axis. So for that we just have to replace y by negative y. So these are the some tricks we already know, and we can use this fact here, and by using this fact you can see that this is not equal to f of x, this value is not equal to the original function, and this value is not equal to the negative of the original function. So it's not symmetric with respect to x-axis, y-axis, or origin. So that means it's neither even function nor odd function. The function is neither even nor odd function. Find the first derivative, use the power rule, and then first derivative would be 2x minus 2. Just use the power rule. Find the second derivative. Second derivative means first derivative of this, which is 2. So as you can see that second derivative is positive, so the graph of this function should be always concave up. But before that, let's find out the critical points. Critical point means where this first derivative would be 0. That is the critical points. So here we know the first derivative is, we need to find out where this first derivative is 0. That point is called critical point. Okay, so just equate 2x minus 2 equals 0 and solve for x. That will give you x equal to 1. So x equal to 1 is a critical point. Now we need to find out where the graph has local maximum or local minimum. So if we go back here and then we our notes, if we go back here, we have one test. It says if your first derivative is 0 at some point and if second derivative is positive, look at this number 2, then f has a local minimum at that point. F has a local minimum at that point. So if the second derivative is positive, the only possibility is local minimum at that point. So as you can see here in this particular problem, the first derivative is 0 at 1, and then second derivative is, if you find out the second derivative of this function, which is 2, which is always positive. So even at that point the second derivative is positive. So at that point you will have local minimum value but not local maximum. Okay, so there is no local maximum, the only local minimum is possible. So the local minimum is at x equal to 1 by using a second derivative test. And then type an order pair, so we have to type 1, which is x value, and then we need to find out the y value by plugging the x equal to 1 here in the given equation. So if x is 1, then what is y? Y is x squared minus 2x minus 8, which is basically 1 minus 2 times 1 minus 8, which is 1 minus 10, which is negative 9. So at 1 comma negative 9 we will have local minimum value. That's perfect. The second thing, identify any local maximum. There is no local maximum because the second derivative is always possible, always positive here. Second derivative is always positive. Okay, so let's go to the next question. Identify where the curve is increasing. So remember, for finding the where curve is increasing or decreasing, we need to find the critical points, and we already know that the critical point is x equal to 1. X equal to 1 is the critical points. So we need to find out where, on this interval from negative infinity to 1 and 1 to infinity, what happens to the first derivative. So we know the first derivative is 2x minus 2. So if we try to find out the first derivative on this interval, it will be negative. And if we try to find out the first derivative on this interval, it will be positive. For that, you can just take some testing point. For example, from here you can take 0, and from here you can just take 2. Find out the value of the first derivative at 0. That will give you the negative value. Find out the value of the first derivative at 2, and that will be the positive value. Meaning the graph of this function would be increasing on this interval and decreasing on this interval. Okay, no, sorry, it's opposite. It's increasing if the first derivative is positive, if it's decreasing if the first derivative is negative. So it's decreasing here and increasing here. So the answer is the curve increases on an open interval. So this is what we need to choose, because there is an interval where the curve is increasing, which is from 1 to infinity, and there is an interval where the curve is decreasing, which is from negative infinity to positive 1. So it's about the first derivative. If the first derivative is negative, the curve is decreasing. If the first derivative is positive, the curve is increasing. Okay, well done. Let's go to the next step. Find out the inflection point. The inflection point means, remember, where the second derivative is either 0 or does not exist. But if you go up and if you see the second derivative always exists, and that's always 2. So there is no place where the second derivative is zeros. So that means there are no inflection points. Okay. Identify whether the curve is concave up or concave down. So for finding the concavity, if you go back to our notes here, for finding the concavity, we can always use this thing, concave up, concave down, by using the second derivative test. Where is that? Here you go. If the second derivative is positive, then curve is concave up. If the second derivative is negative, then curve is concave down. So in this case, second derivative is always positive, so it's always concave up. The curve is concave up, and the curve is concave up on the interval, so it's concave up everywhere. So that means from negative infinity to positive infinity, the curve is in concave up everywhere and is never concave down. Vertical asymptote, this is a polynomial function, so there is no vertical asymptote, so you can just say there is no vertical asymptote. And even it doesn't have any asymptote, it doesn't have horizontal, it doesn't have oblique asymptotes. The asymptotes, if you are playing with the rational function, then you need to find out the asymptotes, but here you don't have any asymptotes. The function has no asymptotes. If you have asymptotes, then that would be that will be helpful for plotting the graph. There is no asymptotes for this polynomial function. Polynomial function, they don't have any asymptotes. So I choose no for vertical, horizontal, and oblique. So now we have couple of information, like we know the curve is a concave up everywhere. We know there is a critical point at x equal to 1. We know the curve has local minimum value at -1, at 1, -9. So we already know so many information. At 1, -9, the curve has local minimum value. Curve is concave up. So so let's summarize the result here. So our summary, we know at 1, the curve has local minimum, so the curves should be go up from here. Okay, so the curve should be look like this, because we know the curve is concave up everywhere. So we just compare our finding with the given options we have. This is concave down, this is concave down, so options A and C are gone. The only option we have available which matches concavity is B and D. But if you look at B option here, the B option has a local minimum value at negative points, so that is not right one. So if you look at the option D, you can see that the local minimum value is at +1, and which is -9. So this is 1 comma -9. That's why the only possible option is D. That's right. So we have graph, we just have to choose from the options, and while choosing from the options we need to use all this information. And now by using this graph, we can say that the function has absolute maximum value. Actually there is no absolute maximum value, so we need to choose second one. And then finally the function has absolute minimum value. As you can see that the value itself is -9, we already know, and it occurs at x equal to 1. Okay, so we are done. So these are the steps we need to follow, and whenever you do this problem, they give you step by step question. You just have to answer that question, and finally you have to choose a graph from the options.